Next, we come to theoretical explanation, at least qualitatively, of why the inverse sprinkler behaves the way it does. That is, why will it turn in the direction opposite to the direction turned by the sprinkler in the normal mode, and why its angular velocity is so low as compared to the normal mode. For that, we consider an L-shaped sprinkler which is completely submerged in water inside a tank. The pressure of the water is assumed to be P1, which is much higher than the pressure inside the sprinkler. Initially, before initially we consider a wall has been placed in the inlet. Thereby, the force exerted by the water pressure, cancel each other out, and while the wall is still there at the inlet, there is no net force or no net torque acting on this system, and the sprinkler remains as it is in a state of rest. However, when we remove this wall, the water starts flowing in, and that's when the sprinkler will start rotating in in this particular direction. So we will concentrate on this part. We will be enlarging it and analyzing it further. Here we see the enlarged portion of the sprinkler. This is the outside where the wall was kept and now has been removed. External water pressure is P1 and the pressure inside the sprinkler is P2, where P2 is less than P1. Initially, due to the pressure difference, it is to be noted that the sprinkler can no longer remain in equilibrium because the wall on which the water was exerting the pressure at the inlet is no longer there. So due to this pressure difference, there will be actually be a force acting on the sprinkler and therefore a net torque in the direction. So if the water is flowing in this direction, the sprinkler will start rotating in this direction because at this cross section area, the pressure is P1 and here the pressure is P2. So as P1 is greater than P2, the sprinkler will start rotating in this particular direction. However, after some time, when the steady state flow is established, there is another consideration that has to be taken into account, which is the momentum transfer by the uh, water to the wall of the sprinkler. So when the water flows into the sprinkler, it has to turn at this particular bend of this sprinkler arm. So due to this transfer of momentum, which is in a direction opposite to the direction of the pressure forces, there is a decrease in the angular velocity of the sprinkler. And in fact, in steady state, we can find out the force due to the momentum transfer, that is A times P1 minus P2, is actually equal to what we have due to the pressure forces. That again the same, A times P1 minus P2. So these two forces balance each other out, and in the steady state, the uh, sprinkler will rotate with a constant angular velocity. But initially, as the due to the pressure forces, it began to turn in this particular direction. It will continue to rotate in that particular direction also in the steady state, which is explained over here. So we can at least qualitatively conclude that in a reverse sprinkler, uh, at least in a steady state, it will experience no torque. Uh, However, when the flow is just about to begin, it will pick up some angular momentum opposite to the direction of the incoming fluid because of the difference in internal and external pressure, due to which it will turn in a direction opposite to that of the incoming. So we find that not only does the direction in which uh, the sprinkler turn depend uh, on these two factors, but it would also depend quite significantly on how the uh, sprinkler is actually designed. In fact, it is possible to design sprinklers so that it turns only in a normal sprinkler mode or in the inverse sprinkler mode, or it will not even turn at all. It is possible to do so by configuring the geometry. So this seemingly answers the question of which way the inverse sprinkler turns, which we gathered from the literature. However, we decided to go a little further and quantitatively investigate the fluid flow inside the sprinkler arm. So we have tried to analytically model the fluid flow through this sprinkler arm, and then we have tried to simulate it. Here we have one arm of the sprinkler which we are trying to analyze. We are assuming the sprinkler arms have been kept symmetrically about the sprinkler head, so that if we analyze the fluid flow through one arm, we can get a rough estimation of the uh, rotation of the entire sprinkler. We have assumed in this model that the sprinkler is already rotating clockwise with angular velocity omega and an angular acceleration alpha. Over this is the inlet and this is the outlet. Water flows through the inlet and goes out into the sprinkler head through this outlet. In order to analyze the flow, we have considered two coordinates. One is the xy coordinate centered at O prime, another is the r theta coordinate centered at O. The length of the tube is L, and in this circular bend, inner and the outer radius is R1 and R2 respectively. XY frame, as I have described over here, is a lag fixed bend. It is an inertial frame of reference. At this particular moment, the sprinkler arm coincides with the inertial frame. However, this r theta frame centered at O is not an inertial frame. It is a non-inertial frame of reference, which also rotates with the angular velocity omega and angular acceleration alpha along with this sprinkler arm. We have considered a material point P, a small fluid particle at a distance r and at an angle theta uh, in the bend of the tube in order to carry out our analysis. So first we have tried to figure out the velocity field. So the velocity of that particle P is given by the standard equation. So if we calculate out the individual terms, we will find this out. Here, of course, VR represents the velocity of. Here, one thing we have to note is that omega r, as I described, and the only thing that is unknown over here is that VR. Here, the VR is the relative velocity of the fluid particle with respect to the non-inertial frame of reference. So, if we plug all this in, we will get that the velocity field with respect to the inertial frame is given by these two equations. However, in these two equations, VR is an unknown. So we have to calculate what is VR. In order to do so, we make the important assumption that the flow is both incompressible as well as invisible. We can safely assume so because we had already previously seen during the experimental analysis that the forces due to the viscous forces exerted by the water is negligible compared to the pressure forces and any other forces. So as it is inviscid, it can also be safely assumed to be rotation. And therefore, we can write out these two particular equation. This equation is for the flow being irrotational, and this particular equation is for the flow being incompressible. So if from these two equations we will get two partial differential equation, and if we solve them simultaneously, we will get the value of VR. So if we plug the value of VR into the expression of Vx and Vy, we will get this expression, where C is an arbitrary constant. And if we describe it in terms of the polar coordinates, we will find out the azimuthal velocity will be given by this expression, omega r plus C by r. Also, V by the radial component Vr is equal to 0. And as it is a planar problem, Vz is also equal to 0. That is, there will be no flow in the direction perpendicular to the plane of the sprinkler. One important thing to note about this is that at roughly low angular velocity and small radial distances, the first term can be easily be neglected as compared to the second term, that is C by R. Next, we have tried to calculate out the pressure field, the pressure distribution along the base